record on this and stop me and ask me a question or two if you feel like it. Yeah. Okay. So recording. Yes. Okay. All right. So let's start with the diagram here. We're going to look at the real number system. So the real number system is like a kangaroo. It has pouches, and then it has kangaroos in the pouches, and there are more pouches in those little kangaroos, and then there are more kangaroos. So it's like the real number system is not like a turtle on top of a turtle who's on top of another turtle. It's kangaroos all the way through. So yeah, kangaroo, that. So if this is the set of real numbers, actually I'll just put in real numbers. And the notation is and the kind of numbers you find in real numbers look like this. You'll have like the irrationals. So I'll throw that in here. Here's an irrational. Here's another irrational. Here's a repeating, terminating real number. Here is, these two are non-terminating, non-repeating decimals if you look at that. A real number also has rationals like 3/5. A real number also has things like 1. Okay, and then let's see, and then we have integers. So integers are z, and these guys are -1, 0, 1, 2. And then we have a set of natural numbers. I'm not doing this well. I didn't think it out. Is this set right here? So natural numbers is a subset of the set of integers. Integers has negative numbers and 0 in it. Natural numbers start at 1, 2, 3 forever. And then there are numbers that are missing from this picture. Otherwise, we would have just used integers for the rest of our lives. And these here we have, let's call this set here set of irrationals. And then this and all of this is the set of rational numbers. So rational numbers are Q. Irrational doesn't have a letter to go with it. So if you take the Q, rational numbers, add them to the irrational numbers, you get this. Okay, so that's some weird kind of picture. All right, let's move on. So let's start with how do we represent real natural numbers, the smallest set of them all. So here we go. Every number that I put on this line is a real number. Okay, but it can also be seen as, so I'm going to put this guy here, 0. This is not the set of natural numbers, but 0 tells us that on the left-hand side, we have negative numbers. On the right-hand side, we're going to get positive numbers. Natural numbers are only positive. So our first natural number is, and it's in red, 1, 2, 3, dot, 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 dot to infinity. This keeps going forever. So what you see here is that this set here is the set of natural numbers. And we find it embedded in the real number line. Okay, so we can say that n is a subset of R for sure. Okay, and then if we try to do some operations like addition, you take two natural numbers, you add them, and the number that you find will always be in this set here. If you take 2 minus 3, if you do subtraction and you get a negative number, you find that minus 1 is not in, this is the in sign, in set of natural numbers. So subtraction fails. Subtraction fails. 2 minus 2, not in set of. You look at the number and see if it's in here. Is it? And turns out no, no.
So, but it does succeed.
Adding. Then it will work. If you do 3, very good. Yes, 1 belongs to. But if you did this business, all the numbers were the same. You take two of the same natural numbers, subtract them, you get 0, 0 is not there. So which means that we need a set that has more than just positive numbers. Okay. Also, division doesn't work, right? You divide 3 by 2, you get 1.5. This is not in there, and this is not in there. Both of these do not belong to set of matches. So division fails, multiplication works.
Multiplication works all the time.
Yes, but not all the, yeah. Very good. All right, so here we go. And so we're going to expand that, and we want 0 in our set. We want the positive. I'm going to put 0 up here, and then all right. Now this set will work with oh, sorry. So this set is now Q, not Q, sorry, Z. Now, one way to also represent this is I could make this line red as well. No, I could just get rid of this guy here and put Z. Okay, so, and here I could also do this. I could put, actually, let me put it in this color.
That number line, to one of them,
are
those numbers still real numbers?
Here's the thing. If we did this, then we are saying that all we know about numbers is that there's only natural numbers. And there's no real numbers. If I put R here, then I'm saying that only this set is represented by the numbers in red and these bars.
It's filled in now.
Everything else is there. All the real numbers are here, irrational and rational. And also, yeah. And over here, we are saying that if I put the Z there, then I'm saying that so the set of integers, Z, is a set of discrete numbers. They jump. There is nothing between 0 and 1. There is no integer between 0 and 1. In fact, there is no number between 0 and 1. If I did this, then I'm saying that I have a real number line on which I've embedded the the integer. And between each of these integers, that actually works. Between, see the set of integers, between each of these integers are zillions and zillions of real numbers. Okay.
So it's more like a partition.
Yeah. And mostly we just work with this real number line. This is just for the first day of for math class where we go through, because the most important two sets are the set of natural numbers and the set of real numbers, because that stays throughout the course. In calculus, you're using this for index numbers, you're using this for counting. You want to know if real, so for instance, set of rational numbers, the idea of a countable set and uncountable set, you need these. You need integers, you need the rational numbers and all of that to think about that. A set is countable, an infinite set is countable if you can put that infinite set like this one. Set of integers is infinite, a one-to-one relationship with the set of natural numbers. You can put, in other words, you can just do this, right? This is going to be one-to-one relationship with 0. 2 is going to be with -1. 3 is going to be with +1. And you can keep going. 4 we go with, right? Yeah. And this will continue. So in other words, this set Z is a infinite set, but countable. Because we can put it into one-to-one correspondence with the natural number, which also goes forever to infinity. So you can't do it with real numbers, but you can do it with rational numbers. Yeah, and the proof is the diagonal proof that you might have seen. Okay, now let's keep going. Now what happens? So subtraction works, addition works, division fails, and multiplication works. And division fails because if we divide 2 with 3, then we look at the set of integers. So I took the integer 2, and maybe I took -3. I did that. I put it in this form, or its decimal equivalent. I'm not going to find this or its decimal equivalent right here. So because this set only has -2, -3, -1, 0, 1, 2, 3, forever. So therefore, in order to do division without freaking out, we have to add the fractions. And so now we're going to do this. And in fact, we can't really do that. Okay, let's try to represent. No, we can't do that, but we can. Yeah. Okay, so what we do is we're going to do this. So we're going to actually have the definition, and then we'll come back to the picture. So the definition is just like integers were created by adding negative numbers and 0 to the set of natural numbers, Q is made up of integers. So Q is a number that looks like this, where it's decimal, where M and N are both integers, which means they can be negative, positive, 0, except where N is not equal to, because division by 0. Now, the cool thing is, what this means is this number, as in like a fraction like 1/2. That's why this is also called quotient. Yeah, so this is the set of rational numbers. Ratio now. Okay. And this, of course, was integers. I forgot to do this. integers, and this set here is called set of natural numbers. Okay, now this means it's these two things here, right? Terminating decimal. We can represent a fraction. If you can represent a fraction as a terminating decimal, or if you can represent a fraction as a repeating decimal, these two guys are also considered to be rational numbers, because these are just different representations of a fraction that looks like that. If you have a non-terminating, like pi does not terminate, square root of 2 doesn't terminate. If you have a number, for instance, this is a fraction that can be represented as an integer over integer. This is an integer. So is this. If I put square root of 2 here, can I represent it as a fraction? Sure, I can put 1 here. Is this a rational number? No, because this is an integer. The definition says the numerator and denominator have to be integers. This is, of course, it's an integer. Is this an integer? No, because this is an, if you actually took the square root of 2, you get a number which is something like this, non-terminating decimal, not a terminating and not a repeating decimal. So you can't. So therefore, this thing here, the square root of 2 is a irrational number. So square root 2 is an irrational number who doesn't have a rational representation. Any number. Is 2 a rational number? Yes, because you can put 2 over 1 without changing the value of 2. The left-hand side is equal the right-hand side. And if this is our m, and if this is our n, 2 is an integer and 1 is an integer. Yep, as long as n is not 0, because the condition is right here. Okay, now, so this is the formal definition that we actually use all over the place, this definition. And if you look at the, so I have finally, actually, I recorded and it's on my list. The square root of 2 is not a rational number. And it's a good, I did a good presentation on that. Now, when the Greeks got to, they were still using, actually I needed to delete this one here. The Greeks were, they thought the world only had rational numbers. So, and so if you did things with distances, you'd only get rational numbers. You wouldn't get pi and square root of 2 and things like that. That freaked them out. So, yes, Pythagoras. So then they murdered him. Yeah, and then he disappeared. So for instance, if you put a stick that is unit length 1, and then you put another stick of unit length 1 here with the angle of 90 degrees between them, this length here is, this length is not a rational number because of the Pythagoras theorem. If you have a 90-degree angle and you know the length of this and this length here, let's call it L. L equals the square root of this side squared plus this side squared, which is square root of 2. So actually, my picture is wrong. This would fall, let's make it again here, fall right here somewhere. Yeah, 1.41 something. So it'll be right after 1. And this length freaked them out. They're like, oh no. We have the formula to calculate the third side. And this is like the simplest of the triangle, length one, length one. The legs are length one. They were expecting a number like maybe 2. They didn't. They got this, and they freaked it out. It freaked them out because they knew this was not a rational.
What they couldn't figure out was wanting to be able to adjust the scale, right? So you have 1, 2, 3, 4. You be able to measure it by something. Adjust the scale to get output.
Yeah. And also, I think their philosophical view was that maybe the world was discrete. Was discrete, not continuous. So, because it was it's a sect. Yeah, they were like Newton trying to discover God in the evening. Okay, and I think other than this picture here, maybe I can, let me just fix that. So here we go. And let's pretend that the length goes up to here. And from here to here, it is 1.41 forever. Okay, is there anything else? Nah, I think that's, so one other thing is, so we can now make this, so n is a subset of integers. Integers are a subset of rational numbers. And n is, and z and q is a subset of the real numbers. And real numbers contain both irrational and rational. And before we end this, let me just draw a picture in which all kinds of numbers are sitting on the rational number line. So I'm going to throw in a half here. I'm doing R. Yeah, so we got the real number line, and I'm throwing in, I started out with a set of integers, -1, -2, all the way this way, 1, 2, 3, all the way to that way. Then I put a rational number represented as a fraction. I could have also put that in here as this. This rational number is also a real number. Every number here is a real number because it's the real number line. There they are. And then this thing is square root of 2 right there. E is 2.7 something. I always forget. So Euler's number is right here. And pi is 3.14 something. Yeah, and so that goes right here. Okay, all right. And I think we're done with that. So, and then if you watch the, yeah, there it is. This picture actually better. All right, I'm gonna kill this session. Is it 1.141?
4, 1, 5, 6, 7.
All right, so that looks good, huh? Up there, 1.14,
1.41.
1.41. It is 41. Okay. Oh, screw it.